Okay, well, thank you everybody for coming. So just I know most of you, but for those who I haven't met properly, I'm Daniel Beckett. I've had about 10 years experience in industry electronics design, predominantly in analog electronics. It's all good. But with microcontrollers and firmware thrown in there as well, a bit of software. This is my first talk class, so appreciate you guys being guinea pigs in this one. Hi, mate. That's all good. Yeah, so we've only literally just started anyway. So what are you going to learn this course? So I'm going to aim to keep it for about 6 weeks. And we're going to learn predominantly about Proteus, how to set up Proteus for professional designs, schematics, that kind of thing. You're going to learn how to make devices and footprints. An important distinction there between sort of what a device and what a footprint is, but I'll go into that later. You can't really learn Proteus without learning a bit of basic layout technique as well. So this isn't a PCB layout course, because that's just a whole different kind of worms. But I'll go through very basic stuff as we're creating a circuit. And then you'll learn what Gerber files are, which is what you need to send, which is what you'll extract from the software, and they'll get sent over to the manufacturers, and that's how you create PCBs. And the BOM is the bill of materials. So that's essentially, you generate a list of components and where you can get them from, so you can easily buy the components for your circuit as well. The class structure, so I'm going to give a bit of a presentation first, which is going to be split between a bit of background of what we're going to talk about, and then I'll do a demo of something. You can, like I said before, you can follow along now if you want, or you can hang fire after I've finished and then do it then, or you can take it away. I'm going to email everybody the slides anyway, so you can do it at home, or come grab me in my office, whatever you want to do. Questions are welcome. If you want to ask me something during the course, if something's confusing, ask me. I might not know the answer. If I don't know the answer, I'll find it out and tell you next week. And at the end, we hopefully will end up with a working Class B headphone amplifier. So that's kind of the thing that we'll make. I've not tested the circuit yet, so I hope it'll work. We'll see. But it's actually quite an interesting little dive into the shortcomings of Class B amplifiers and what you can do to kind of improve them a little bit as well. And you end up with a headphone amplifier, so that's pretty cool. So first section, a bit of introduction on kind of circuit board technology and where we've come over the years. And I spend a bit more time on modern circuit boards and where we are today, because it's a huge subject. So can anybody spot the PCB on there? No. So this was, I'm guessing, around 1950s, 1960s, point-to-point wiring. It's going to be difficult to diagnose a fault on that board, as you can probably appreciate. And you're probably not going to pass EMC standards on that board either. Not like EMC even existed then, but and it's going to be quite difficult to make many of those and sell them and ship them and test them. That's a bit of a close-up screenshot of a 1930s radio with an air core inductor wound across that. A bit of Bakelite, a few wires. So moving on from that, we developed, I think, around the 1950s, got popular in the 1960s, WireApp. So what this is your components sort of go onto your substrate, like your PCB, like FR4 or fiberglass kind of substrate, and then you use these little pegs to connect to the legs of the components, and then you wire wrap, a stripped bit of wire around the pegs. Now, you can semi-automate that task using machines to wrap. The use of it kind of peaked in the 1960s. It's sharply declined now because surface mount technology has basically overtaken this completely. But it did have some benefits over PCBs at the time. Namely, they're less prone to fail due to shock and vibration because you haven't got these rigid structures that are soldered on, that you can get a bit of flex in that, and it's not going to snap the components. There's no solder joints on here, so they're less prone to, well, they can't. You can't get a dry joint or a cold joint, or you can't get solder corrosion because you haven't got solder there. And there's actually lower electrical resistance in a connection like that than there is a solder connection. Yeah?
What's a cold joint?
A cold joint is when you haven't heated the solder up enough and it's enough to flow over the two pieces of metal that you're trying to join together. So it's essentially a higher resistance solder joint. You're not expecting it. This avoids that due to an effect called cold welding. Has anyone heard of cold welding? Do you know what you've heard of it before?
Well, I can guess what it is, but I have heard of it before.
Yeah.
So it's like just basically a really good contact, and it sort of welds. It's like a sort of a weld basically without heating it.
Yes. Yeah. Yeah. You could have guessed that from the name, couldn't you? Yeah, exactly. So what happens is, this happens in space quite a lot. If you've got a very, very clean metal surface and another perfectly clean metal surface, and you bring them together, they all of a sudden start sharing electrons. And when they start sharing electrons, they become one material. So you get an extremely strong, perfect weld in the absence of all contamination, all oxidation. They just go, that's it, you're screwed. It happens up in space, and it's actually a problem sometimes.
I think they had it unmasked with the TF joints.
Oh, really?
Yeah, they put them together, and they were there for 18 months before we put any current through them. And now they've stripped them out and found that they were very, very stuck together.
Yeah.
Not moving quite as well as they wanted them to.
Yeah.
And clean them all up.
Yeah, especially if the surfaces were prepared beforehand.
Yeah, completely clean and everything put together.
Yeah.
Under pressure.
So it does happen. Like and in these situations, in that situation, the electrical connection is very, very low resistance, extremely low resistance. So that's what happens with these. So this is a picture. Can you tell that they're all twisted pairs? Can you see that?
Yeah.
So this is actually a mainframe computer. It's called a KL10. This is the backplane of it. So this wasn't done by hand. It would have been very impressive if it was, and I'm sure there are some people who've done this kind of work before by hand, but this is semi-automated. And yeah, it's WireApp, twisted pairs. The computer is sort of in service from 1966 to 83. So that's where that technology went. So now we move on to actual PCBs. So you used to have essentially like a draftsman who would draw out a PCB on a sheet of mylar, which is transparent plastic. You would then, I'm just thinking about the microphone. So this guy would draw this circuit board out on a piece of mylar, transparent sheet, about 2 to 4 times the size of what it would be on the PCB. That would then be used in a process called photolithography, where you get a copper-clad board, solid copper, sort of FR4 on the back. You would put a photoresist on it, and then you would use this mylar drawn sheet, and then you'd direct light through the sheet, use it as a mask, and then you'd expose all of the photoresist that the mask doesn't cover. And you can use lensing to shrink this image down to the size that you want, like an overhead projector, that kind of stuff. And then once that process is done, you've got a PCB. So you've got a PCB like this. That when you put, no, actually, probably negative actually. So where the mask, where the mask is, that's the part of the circuitry that get protected. When you put it into the acid to etch it, you bring it out, all the copper's etched away where the solder is. And then that's how you've essentially printed your circuit board. So that's kind of like what it looks like once you've finished with it. Can anyone tell me what the hallmarks of a hand-drawn circuit board are? How can you tell that was hand-drawn?
Wavy lines.
exactly. So all modern packages basically draw angles at 45 degrees. So moving forwards now, so we're going to move on to EDA packages, electronics design automation. So this is things like Proteus. So these packages take care of both the schematic and the layout side of things. So this is essentially a simple modern schematic. I think this was done in Eagle, it looks like it was. And some of the features to note on this. Okay, so what we've got, all the purple boxes are ground. That means all those nets are connected together. Every single ground net is connected together. It means you don't have to wire wires to every single point. It makes schematics a lot neater. You've got standard icons, graphics for each component. So you've got MOSFETs, capacitors, and resistors. These resistors are actually zigzag lines, and that's kind of like an American standard, whereas in European Union, Europe, we use boxes. Yeah, exactly. The IC pins, you can display the number on them if you want, so that makes it a lot easier to kind of like, do the schematic whilst you're doing it, and then especially when you're debugging. And then you've got reference designators. Does anyone know what a reference designator is?
Is it like for referencing to other drawings, perhaps, or?
It's actually not. It's to reference the schematic to the layout. So the reference designators are, it's dead simple, this one. Q1, IC2A.
To the screening
Yeah.
on the PCB.
Yeah. So you can go on your silk screen on your PCB, you can see where that component is and see exactly where it is on here as well. Just identification. And what does that produce? That produces something like this. Now, what are the hallmarks of a circuit that has been designed in an EDA package? How can you tell that's been done by software?
It's neat.
What's that?
It's neat.
Neat. Yes, it is neat. Particularly the resistors, all of the packages of the resistors are identical. Yeah.
It's all right angles in 45 degrees.
Yeah, exactly. So 45 degrees, you've got these traces that aren't wavy lines anymore. Every single one's like a perfect angle. And you've got font on there as well. So, yeah. So moving on to slightly more complex designs, this thing, so I pulled all this stuff off the internet. This is a more complex schematic from 2008. And it's a neural network motion control system for a robotic arm. And the neural network in this instance is used, you can think of it as like a self-tuning algorithm. So if you don't know all the values for like PI and D control on plant, neural networks can actually just self-tune, basically. It sounds well complicated, self-tuning. It is complicated. I don't want to take anything away from whoever designed this.
Easy.
Yeah. One other thing to note as well. You see these blue lines? What are these blue lines?
Boxes.
Yes. So each one of these, that D0 to D7, that contains 8 lines on a bus. So you don't have to have a horrible ton of lines all over your schematic. Yeah, it makes it neater and makes it easier to understand it. So this is not the same circuit as the one previously, but it does demonstrate a lot of the modern techniques that we've got in EDA packages and tools available to us. So it's multi-layer. So how can you tell that circuit's multi-layer?
Different colors.
Yes. So there's loads of different colours. You've got like orange, green, pink, red. So it's, multi-colours, multi-layer. They've got a load of vias on there as well. Now, a via is a tiny little hole drilled through the circuit board, and then it's got a tiny little plated barrel. So vias connect layers together. You need some way to connect layer 1 to layer 4. That's the way that you do it. And the vias are actually, you see these little bright green dots. And you see all these tiny little dots. They're all vias as well. So they're all perforations of the circuit board connecting layers together. Has anybody heard of a BGA package? No. Right. BGA stands for Ball Grid Array, and it's the most dense IC package that you can get, really. And what it means is, it means that you've got, so all these pads here, that all belongs to one IC. So instead of the pins coming out the side of the IC, all the pads are on the underneath of it. So you've got many, many connections underneath the thing itself. Other features that you can see here. Can you? Yeah.
How would you solder that?
Guess. Have a guess. What do you think? What do you think you could do to solder that on? If you can't get a soldering iron in there.
Heated. Should be just.
Oh, look.
Yeah.
Machine process, won't it be?
You can do them by hand.
In the kitchen.
Yeah. So basically, you pre-warm the PCB so it's not stone cold, and then you can. There's a few different methods to do it, but you get some heat source. It could be infrared, it could be air or whatever, over the top of the package, and then you heat the whole thing up to soldering temperature, basically. And the entire thing's red hot, and then the thing just goes.
But the IC is able to take that. It's
Yeah.
yeah.
Yeah. ICs and components all come with reflow profiles. So in all, industrial automation, you'd actually put it in the one end of a conveyor belt, and then it'll be in a big long machine that gets zoned, and it's like zones of heat. You know what I mean? And then that takes it up in temperature, soaks it at high temperature, comes down at a controlled rate, and then by the time it comes out of the conveyor belt, it's soldered. So, one other thing, there's probably reference planes on here as well. So reference planes are solid planes of metal that are either ground or power, but I don't think they're visible on this drawing because otherwise you'd just have blank. Wouldn't really you'd be able to see, they're transparent on these designs, but obviously to see the traces, you just hide the reference planes. BGA, that's what it looks like on the underside of it. An interesting note, actually. Imagine if, like, that pin doesn't solder properly. You know what I mean? What happened with the Xbox 360? People were getting this thing called the red ring of death. Has anyone heard the red ring? Yeah, okay. A few gamers, right? And what happened was the graphics chip in the Xbox was getting hot and cold and hot and cold and hot and cold. It brittled. It made the solder brittle underneath one of these BGA packages of the graphics chip package. One or two of the solder joints disconnected. The thing just wouldn't boot. So I used to buy them off eBay, put them in the garage, get one of these heat things, and resolder them and sell them on again. So this is what the actual board looks like of the BGA package. You can see the pads, which are the shiny silver bits, and you can see all the vias, sort of perforated within the package. There's this thing called fan-out. These two top rows, you can see that you can route the traces into the package from 2 rows. Whereas if the next 2 rows, how are you going to route those traces out? You've already taken up all the space on that layer. So you had to access the next 2 rows in. So these 2, you have to go to another layer, and then you have to go to another layer, and another layer. That's how you access these things on these.
What's the current limit on those? The number of layers you can do that in this type of technology then?
There are some boards of 36 layers. So the current limit would be determined by the copper thickness of each plate, of each layer. And you can essentially double up or multiple vias to increase current as well. But in terms of layer count, you can get up to 36 layers on these boards, and maybe even more in certain circumstances. But it's just crazy. We're not going to start with 36 layers on. So what would essentially a modern computing hardware look like from a routing perspective? Like that. So this is a board, a computing board. It comes with PCIe 2 interconnects lanes, DDR3 memory, fast Ethernet connection, and some more connectivity. So you can see it's extremely complex. Now, why do we need these kinds of boards? Why do they exist? What's driven them? So computing over the years, as everybody knows, has got more and more advanced. Things like your mobile phones that have boards in like this. Like these things are extremely advanced. Telecommunications requires extremely high speed and massive bandwidths of data. So you've got gigabytes of data floating through the air, and all that information has to be processed at network switches and sent out across transatlantic cables and satellite communications. You've got extremely precision timed devices in satellite communication devices, especially with GPS. And high-speed data acquisition. So experiments like the LHC in Switzerland, every time that they collide some atomic particles together, they create a vast amount of data that they need to process. LIGO in the US, detecting gravitational waves using very sensitive interferometers, incredible amounts of data, and here as well. So JET, for example, produces a huge amount of data every time we do a pulse. All that data's got to be saved, read, and then processed. And we've got supercomputer clusters for scientists to churn through that data and turn it into useful information. So that's why we do it. Okay, so don't worry, we're back to Proteus. So what I'm going to do is give kind of like an idea of what packages are available. So we've got Altium, EasyEDA, Eagle, KiCad, OrCAD. We're using Proteus. There's lots of different ones out there. The reason why we use Proteus is, I mean, it's quite well used in the UK because it's a UK company who design it, and it's quite easy to learn. So the entry level is quite easy to get involved with, and the UI is quite intuitive. Some of these packages are very expensive. Some of them have features that we just won't use. So Proteus is a good one to use. That's where they're based. So in the Yorkshire Dales in Grassington. All right, so Proteus is a program of two halves. This is the schematic side, and then the other side is essentially the layout side. You have got different tabs in there, but these are the two main places that you'll spend most of your time designing in. Stuff that you have to be aware of. You can see that the menus are different. That depends what tab you've got open. So if you've got your schematic side open or your layout side open, depending on which tab you've got, the menus change. So just be aware of that. And even if you go to the same menu, so system keyboard mapping, it's the same menu item, but if you're on the schematic or the layout side, it brings up a different window. So the keyboard map here is not the same as the keyboard map here. Right, so the first thing we're going to do in Proteus is create our libraries. So this is going to be your first task to do in Proteus. You need to create libraries. A library is a collection of components, and one IDX and .lib file generates the library that Proteus uses. So these capacitors, all these capacitors here are contained in these two files. And again, this is another way to view it in Proteus. It's important to make a distinction between devices and packages. A device is the symbol, like the schematic symbol, and it contains what footprint it needs. The package is just a footprint on its own. It's a much simple, it's a very simple library. Just to give a visual indication of what that means, I've got four libraries here. 3 device libraries, 1 package library, okay? So the device library contains this chips library contains a microcontroller and an ADC, and it contains all the information about that. So 8 bits, blah, 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 made by Atmel, Farnell stock code. It's got 16 pins. It references the SO16 footprint. This one is an ADC. It also references the SO16 footprint. These resistors and these capacitors also reference the same part. So all I'm trying to say here is that you can have many devices referencing the same footprint. And that's common because devices use the same packages. So the first thing we're going to do is create our own user libraries. So Proteus comes with many libraries and components by default. But there are many components available to buy. You aren't going to be able to, Proteus, you can't have all of them. You're going to have to create your own. If you're trying to create a device and it's not in Proteus, the chances are there is going to be a footprint for it. So search the libraries when you're trying to create a device, because you don't want to just be remaking the same footprints over and over again. There's no point. And they'll have done a good quality footprint as well for you. It comes with only one device library and one user library to start with. That's why we're making our own now. So start as you mean to go on. Sort your libraries out now. You can keep them forever. And you can just keep adding into them. We're going to create 8 device libraries, and we're going to create 2 package libraries. So the first thing you want to do is go into user folders and create a small directory structure. So choose a folder to go in. In there, create one called Proteus, and then create a folder in there called libraries, and then create 2 folders in there called device and package. That's where your libraries are going to sit. Then you go into Proteus, and then you open it, System, Settings, and then within this tab, you click the little plus here, and then this is where Proteus will look for library folders. So you essentially select your device directory that you just made, press OK, go back and press the plus button again, select the package library that you just made, the folder, sorry, and then press it again. Restart Proteus, and now it knows that those directories exist. So now we want to add the libraries to those directories. You select the schematic capture icon, so you bring up the schematic capture screen, and then you go to Library Manager. That brings up a second tab called Device Libraries here, and then you can access the menu Library, Create Library. Again, I'm going to give you these slides, so don't worry if you don't remember all this right now. Just giving you a very quick run through, because it's a pretty simple task at the end of the day. I just want to go through it once with you so you understand it. Once you've got to create library, you literally drill down the menu until you go to your device folder, type in the first library name. So the way that you do your libraries is do your first 2 initials, so and then underscore, and then the library that you've got. So we're going to do capacitors first. And then you just press OK on the initial index size. That sets the initial size of the library. You need to do the same process for each one of these libraries. So obviously capacitors and chips, pretty simple, you know what they are. Electromagnetic. So what components would you put in an electromagnetic library?
Inductors. Relays.
Yeah, relays would go in electromagnetic. Any others?
Contactors, if you've got big contactors, a bit
Yeah.
industrial, isn't it?
Transformers?
Not transformers, but I will go on to the library that will contain that one.
Diodes.
No. So electromagnetic is essentially anything that can kind of move with electromagnetism. So motors would go in there. Obviously your relays would go in there, solenoids, that kind of thing. The next one's a magnetic library. Now what would go in the magnetic library? So that would be your inductors, and that would be your transformers.
Right.
Anything that is essentially mainly inductive, you'd stick in the magnetic library. Mechanical, so any fixtures and fittings that you need to connect to the board, maybe even shielding as well could go in there. And then resistors, semiconductors. Semiconductors are things like diodes, LEDs, that kind of thing. Just simple PN junction stuff. And then you do the same for the package library. So you do exactly the same process, but instead of having the schematic side open, you just open the package, the layout side. Sorry. So you click the layout button, and then when you go to Library Manager, it brings up the package library rather than the device library. And we've only got 2 to make in there. And these 2, so obviously library, create library, and you create SMD. and you create through hole. That's it, just those two. And then every single footprint that you're going to create is either going to go through the board or it's going to sit on top of the board. That will take care of every single footprint that you'll ever need to make. Okay, that's it. Sorry that this first one goes on a little bit. To be honest, the bits of Proteus that we need to do at this point is quite simple, but I didn't want to inundate you with a bunch of tasks to do now because there'd be too much information to take on. So in the coming weeks, we're going to create our own devices, we'll create our own schematics, we'll put that into a layout, and if you get to the point where you've generated your Gerbers, we'll get those sent off and you'll create your own boards as well. So, any questions?
So when we looking to create these libraries,
Yeah.
I'm thinking about how I'm going to try and apply the knowledge I'm going to learn here.
Yeah.
To start with a project, so I'm going to try and make a this. Do I then look up the capacitors and et cetera, that I'm going to need for that and start from that point?
If you were going to create your own project, then you would want to kind of know already. You want to have done quite a lot of the design stage. So you'd have done things like simulations. You'd have done bench testing, that kind of stuff.
Okay.
And then
let me adjust my question.
yeah.
Because what I'm going to do is take some boards that already exist
Yeah.
and redo them.
Yeah.
So look at those boards.
Right.
Find those.
Similar to what Ellen
Yes.
and Cook are doing right now. Yeah.
So, and then create the library from those components that exist on that design.
The libraries that I've just demonstrated
Yeah.
will capture every single component that you'll be able to throw at the board. So you create the exact library structure that I've demonstrated.
Mm-hmm.
All the components that you then need to create in Proteus to copy those PCBs, you'll save into this library structure.
Okay.
Does that make sense?
Yeah.
The library is an empty bookcase.
Yeah.
You just fill it full of books,
Yeah.
which is a component or a footprint. Make sense?
Yeah.
Yeah.
So we're not saying this shelf is this type of project and that shelf is this type
No,
of project. which is-
exactly.
Yeah.
That's exactly right.
Yeah.
Any others? We good? Cool. Well, thanks a lot for coming. Like I say, sorry this first one goes on a little bit, but yeah, next week we'll be.
Yeah, Proteus.